So in this video, we're going to determine the centroid of an area through principles of integration. The first thing you might want to ask yourself is, when will I need to use integration in order to determine centroids? And the quick answer for that is when you can't determine the centroid by symmetry. Remember that some areas will exhibit symmetry, particularly two lines of symmetry, and we know that the centroid is always at the intersection of those two lines. In addition, some shapes occur so common that their centroids are computed for you in a table, and we'll look at how to use that table in order to compute centroids of composite areas in a later video. So in scenarios in which we don't got a table, we can't use symmetry, and one of the kind of bounding curves of the actual area, here highlighted in blue, corresponds to a function that we can integrate, that's when we'll be asked to use integration. So if we look at the shape, the area rather, that we're dealing with here, highlighted in blue, it has a width A, it has a height B, so those will actually be real dimensions in real life, maybe like 14 inches and 3 inches. And at any point along the base, if we want to determine the height, we know that it's defined by this quadratic function here. So if we measure a distance from the thin edge towards the larger edge, if we measure out in the x dimension, if we want to know the height at that point, we just simply use this function. So in terms of what we're asked to do, we want to determine the constant k, find the total area, find the first moments of that area about the axes, and then find the centroid. But before we do that, let's try to get some physical intuition to this. So imagine this were printed on a sheet of paper in front of you, and you actually cut along the quadratic bound and cut out the area that's highlighted in blue. And imagine it was pretty rigid paper. So you could assume that it was kind of like an infinitesimally thin plate that had uniform density. And then imagine trying to balance that in front of you, actually putting your finger under a particular point to keep it balanced. Where would that point be? Because remember, under the assumptions that an area is an infinitesimally thin plate of uniform density, the centroid is just the center of gravity. So hopefully you would see that since the majority of the area in blue here is kind of located in the lower right-hand corner, that's where the centroid is going to be. So if like A were to be 10 inches, maybe it's like in terms of its x-coordinate at 8 inches. And if B were to be, 4 inches, maybe it's down here at 1 inch or something. We're not going to have actual values for A and B, so the answers that we get are going to be fractions of A and B. So maybe it's, 3/5, 60% of A, or maybe it's 1/10 of B. Those are just wild guesses. The really only wrong answer there is anything that doesn't place it down here in the lower right corner, which is where it will be. So what we want to do is define each of these quantities, and the way that we're going to do it is largely based upon the principles of integration. So hopefully all of you have taken a calculus class relatively recently where you've integrated power functions. So first question is, how do we determine the constant k? So we know that the height at any point along the x-axis is given by this function. So when x is equal to a, we can plug in a for x, a squared times k, that is the height. But the key thing is here, we're assuming that we don't know k as a number, but we do know a and b. So we want to express k as a function of a and b. In addition, the special thing about the point x equals a is we know what y has to be. Y has to be b. So the way that we're going to express k as a function of a and b, or in terms of a and b, is we're going to evaluate this function for x equals a. We know that y has to be equal to b. That's all that's been done here. When you plug in x equals a, y has to be equal to b. We can solve this algebraically for k and find that k is simply equal to b divided by a squared. So it might feel that all we've done here is kind of some alphabet soup and juggling of letters, but practically what they're assuming is that you know the width and you know the height, but you don't know the parameter that defines the quadratic bound, but you can express it in terms of those known parameters. So the reason that they've solved for both y as a function of x and x as a function of y relates to the approaches that you can use in order to determine the area and the moments. Both of those are going to need to be determined by integration. Now, why is that? Well, we don't have an expression for the area of we don't know offhand an expression for the area bounded by a quadratic function. If this were to be a triangle or something, we know that we can compute the area as 1/2 times the base times the height, but it's not a triangle. So the way that we compute the area of the areas that are bounded by a function that we can integrate is to break them into simplistic shapes for which we know the area. Most typically, when we're integrating in one dimension, those shapes would be some type of thin rectangles, because we know the area of a rectangle. And we know that in addition, if this rectangle is infinitesimally thin and we slide it underneath the entire curve, for the case of these vertical strips, we can represent the entire area under the curve. So that's just to say that the total area can be found by summing up each of these little infinitesimally thin areas of rectangles. Now, why do they have to be infinitesimally thin? Well, if you think about the area of a rectangle, of course, any rectangle, it's just going to be the width times the height. So if these are infinitesimally thin, dx, imagine that you don't quite get them thick enough and you're trying to compute the height. The question is the height where the rectangle intersects the curve on the right, or is it where the rectangle intersects the curve on the left? Well, those are going to be more and more similar the more and more thin that you make these rectangles. So that's why you have to allow the width to become infinitesimally thin so that the height is well defined as a single point y. But under those assumptions, the infinitesimal area is going to be y times dx. And if we want to find the total area under this curve, we're just going to add up the area of all those infinitesimal areas, and we're going to allow the x-coordinate to slide all the way from 0 to a. So that is going to give us the actual definite integral that we need to compute. So area is the sum of all the infinitesimal areas. Each infinitesimal area has a height of y and a width of dx. Y can be expressed as a function of x, which we're going to need to do since we're integrating at x using the original formula that we were given. Y is kx squared, or expressing k as a function of b and a, it's b divided by a squared times x squared. So this is just substituting in this expression for y as a function of x. Be careful there. Remember that b over a squared is not a function of x, so it is a constant. It can come out of the integral x squared dx. The way that we compute the definite integral is to first find the antiderivative. The antiderivative of x squared is x cubed divided by 3. We want to evaluate that at the upper bound of integration, which is x equals a, and then subtract away the value at the lower bound of integration, which is x equals 0. When we plug in x equals a, we'll get a cubed over 3 times b over a squared. Canceling two factors of a, we're left with b times a divided by 3. Minus the value of evaluating this at x equals 0 is just going to be 0, and that's how we're getting this expression of ab divided by 3. And again, in terms of a sanity check, you imagine if you just drew a straight line from the origin to point B, that would be a triangle with a height of A and a base of B. And remember that the area of a triangle is 1/2 base times height, so it's going to be a little bit less than that triangle because if you draw a straight line, you're missing that little bit of area there that's included in the triangle and not included in the area bound by the quadratic. So how are we going to go about actually determining, using those same principles, the first moment of this total area about the y and the x-axis? And remember that the first moment of the area about the y-axis is denoted as q sub y, and the first moment of the area about the x-axis is denoted as q sub x. Well, we don't know the total first moment of the area about the y-axis of this complicated shape. However, we know if we break it up into a bunch of little triangles, a bunch of little rectangles, sorry about that, that each rectangle, we're going to have an easy time computing its moment. Will begin with about the y-axis. The way that we're going to do that is just take the perpendicular distance from the y-axis to each little rectangle, which is going to vary depending upon where the rectangle is at, but generally speaking, it's just going to be the variable x. And then we just need to multiply that by the area of each little rectangle, which is just going to be dA. So just y times dx. Now, in terms of the formulation here, this x bar L that they're using is just to say that this little rectangle has a centroid that's denoted by x bar L and then below y bar L. And remember that centroids of rectangles are located at the intersections of the line of symmetry. If you draw a vertical line and a horizontal line, they intersect right at this point in the middle. But since this is infinitesimally thin, the x-coordinate at that point we're approximating is just x. So that's how we're getting x bar L just becoming x. dA, we already showed, is y dx, substituting that in, remembering that we need to express y as a function of x in order to do the integration, and we're integrating from 0 to a. Y as a function of x, b over a squared times x squared. Do your arithmetic here. Take the b over a squared out of the integral. Combine x times x squared to get x cubed. The antiderivative of x cubed is x to the 4th divided by 4. Be careful with your evaluation and make sure you can get a squared times b divided by 4. And at this point, you definitely want to pause the video at each calculation and make sure that it's something you can do. The key thing when you're watching these kind of videos through the remainder of the semester, because they're often going to have pretty complex math that's embedded into them, but we can't have like each sample problem be a 30 or 40-minute video, is you want to kind of pause, make sure while you're watching, make sure that you can follow along with what I'm saying, and then pause and then make sure that you can replicate the math. In terms of determining the first moment of the area about the x-axis, We again use the approach of breaking it into vertical strips. In terms of these little vertical strips, the y location of the centroid is going to be y divided by 2 because it's halfway up there. So that's how this y bar L is becoming y divided by 2. Again, y is just, dA is just y times dx. In terms of the arithmetic, we'll pull the 1/2 out of the integral. Y times y is y squared. We don't want to use the variable y. We want to express y as a function of x since we're integrating these vertical bars over x. So substituting in y as b over a squared x squared, and then squaring that entire thing. That's going to give us 2 factors of b squared over a to the 4th. That's where the a to the 4th is coming from. The 1/2 came from the fact that the centroid of the rectangle is 1/2 of the way up. And then when you square x squared, you get x to the 4th. The antiderivative of x to the 4th is x to the 5th divided by 5. Be careful with your evaluation, and you should get that the first moment of this entire parabolic area about the x-axis is a times b squared divided by 10. Now, how would we actually use that to determine the centroids? Well, it's all related to that formula that we showed in the first video. Namely, we can find the x location of the centroid by multiplying by the area, and that quantity is by definition equal to the first moment about the y-axis. So solving this for x bar, remember that the area was the first thing that we determined through integration, a times b over 3. The first moment about the y-axis we determined on the last slide, a squared b divided by 4. And if you solve that for x, you're going to get 3/4 a. So that's just saying that the balancing point in the horizontal direction is in this lower right-hand corner at 3/4 of the width, as we guessed it would be. In terms of the y-coordinate of the centroid, we guessed that it was going to be pretty close to the base here. So maybe like, I don't know, b over 8 or something. It turns out, as you see here, that it turns out to be 3/10 of b. So our results are physically intuitive with what we anticipated. Don't get messed up. Something that messes people up is they say, well, why is this qx if that's the formula that involves a y-centroid? Well, remember that the way you're finding the y-coordinate of the centroid is you're looking at the first moment about the x-axis, or how the rotation is actually induced about this axis. So that's going to be related to perpendicular distances measured in the y direction in terms of qx. Just like qy, the moment about this axis is going to be related to perpendicular distances measured in the x direction. So I know that was like a trial by fire and a lot of stuff to digest relatively quickly, but again, if you need to go back and just pause certain points and make sure that you can follow the integration, feel free to do so. But we will determine centroids via integration when one boundary of the curve is bound by some type of function which we can integrate. In this class, it's generally going to be power-based functions. We broke it into vertical rectangles. You can also approach the problem the same way using horizontal rectangles. There is an example in your text if you want to look at it. The reason that it's more natural to break this into vertical rectangles is the upper bound of the function y is already given as a function of x. If it were to be the other way around, we would break it into horizontal rectangles. You can do it both ways as long as you can solve for an inverse function. That's why if you notice in this original formulation, they express both y as a function of x along with x as a function of y. This would be useful if you were to integrate using horizontal rectangles, but that's not going to be as easy a function to take an antiderivative since it has a square root. So it's all about, you can do it both ways, but easier to do it the way that gives you the easier math.